I look over there, you have to do something there. No. You don't have to draw.
Yeah. The Tucson Amateur Astronomy Association monthly meeting. We have people attending in person tonight, people on Zoom, and people on social media. And we're just delighted to have you all here. Tonight, we have Bob Rose operating the camera, and we have Terry Lappin and Jim Knoll, who is from afar tonight, still helping to operate our computer systems. So I think we're all in good shape for the evening here. I'm Mae Smith, and I'll be chairing the meeting tonight. I want to welcome everyone here, and I want to remind our people who are attending in person that any sounds that you make during the meeting may be picked up by Zoom. And so we ask that you try to be as quiet as possible during the meeting to help our people who are attending through media to get clear messages. So thank you so much for that. I have an announcement for our Tucson Amateur Astronomy Association members. And that is that our regular yearly elections, of course, are taking place now, and that our members have 30 more minutes to cast their votes in the election before the computer shuts down the opportunity. So if you're a member and you've not yet voted in the election process, please proceed to do that right away. We have a wonderful guest speaker tonight. Dr. Dante Lauretta is here, and several of you will probably remember this. He's come several times to talk with us over the years, and he shares fascinating things when he comes. So we're always looking forward to his presentation. He's a Regents Professor of Planetary Science and Cosmochemistry. So it's very, very impressive for someone to be a Regents Professor, but it's also very impressive for someone to be a Regents Professor in those particular specialty areas. And he's also a director of the Arizona Astrobiology Center. So Dr. Lauretta is going to talk to us about OSIRIS-REx and Bennu's secrets unveiled.
Thank you. Great to be here. I love the hometown crowds. Let's get our slides up and we'll get going. Perfect. All right, everybody hear me okay? Thank you. Yeah, so this is an exciting time on the OSIRIS-REx project. We've been analyzing the samples about a year and a half now. And the science is really coming in fast and furious. I'll hit some of the highlights on what we learned. But just to bring everybody up to speed, I'll give you a little bit of background on the OSIRIS-REx mission itself. This is a NASA mission in the New Frontiers program. And it's a mission that targeted a near-Earth asteroid named Bennu. You can see the orbit diagram here on the left. This is the sun. The Earth's orbit is in this teal color here, and the asteroid is in this orange orbit. And you can see that it is a near-Earth asteroid. Most asteroids exist in the main asteroid belt between Mars and Jupiter, but they do tumble in to the inner solar system into a dynamically unstable configuration. Something like Bennu has a lifetime now of about 10 million years before it most likely falls into the sun or maybe collides with one of the terrestrial planets. And Bennu has the distinction of being what we term the most potentially hazardous asteroid. And you get a good sense of the relationship between the orbits if you look at this more oblique view of the relative orbit diagrams. Bennu's orbit crosses that of the Earth in September, typically. And because of its orbit, which is highly elliptical compared to the Earth, you can see it almost gets out to the orbit of Mars and it crosses interior to the orbit of the Earth, making it an Apollo-type near-Earth asteroid. And so its orbit period is 1.2 years. The Earth's orbit is 1 year. So every 6 years, they line up and Bennu does a close approach to our planet. And I don't want you to worry about it being a potentially hazardous asteroid. The odds are still really low, 0.05% of an impact. And if it is going to occur, the most likely date is September 24th of 2182. So we're looking well into the future. Nobody in this room, I don't think, will be here to worry about it. It'll be somebody else's challenge to deal with. The name Bennu was selected as part of an international competition that we did in partnership with the Planetary Society and the Lincoln Near-Earth Observatory, which discovered the asteroid in 1999. And the winning entry was Bennu, which is the Egyptian heron that you can see in the hieroglyph here. And he's related to Osiris. Osiris is our namesake for the mission because, as you'll see, in addition to having this distinction of hitting the Earth and causing challenges for life here, asteroids like Bennu, which is characterized by having a very low albedo or low reflectance, reflecting about 4% of the sunlight that hits its surface, are rich in organic compounds that we think are relevant to understanding the origin of life on Earth and maybe throughout the solar system. So they have this dual aspect of bringers of life, harbingers of death. And Osiris, the myth, also had that dual nature. He has a green skin, known as the god of agriculture, probably an early leader in the Nile Delta who brought agriculture to that region, but also passed on to the afterlife, was resurrected, and he's the one who judges you when you go into the afterlife in the Egyptian mythology. So here's what the target looks like. This is real data from our mission. Give you a sense of scale, the long dimension's about 500 meters. That's about the height of the Empire State Building. Or for those of you in Tucson, if you're familiar with the Push Ridge, the peak on the western edge of the Catalina Mountains is about the same height as Bennu. So it's like a small mountain in outer space. And it has several distinctive characteristics. First and foremost is the shape. It's 500 meters across, yet it's nearly spherical. That's unusual. And in fact, when we first selected the target all the way back now, 20 years ago in 2005, we weren't quite sure about the nature of these near-Earth objects. And the spherical shape suggested that it was probably a rubble pile. And by that, I mean it's a loosely bound accumulation of boulders and gravel and dust held together barely by its own gravitational force. And you can get a sense of the rugged nature of the surface. There's some really distinct boulders that protrude from its surface. Heavily cratered, you can see some large craters, particularly concentrated around the equator. So this thing has been hit multiple times. And from the data, so this is a combination of 3D topographic data from our scanning laser or LiDAR system, as well as high-resolution images from the Polycam, which is a telescope actually built in partnership with our colleagues here at the Stewart Observatory who are hosting us this evening. And you can see the colors are enhanced, or I'd say the brightness is enhanced, because if I showed you the actual reflectance, you'd barely be able to see it on the screen. But I've always said it has this salt and pepper kind of texture to it. There's few specks of really much higher reflectance material that are kind of distributed throughout the surface. And I want you to keep that term in mind, salt and pepper, because we started using that in 2018 when we first were approaching the asteroid to kind of describe the nature of what we were seeing. So OSIRIS-REx is a spacecraft that was built by our partners at Lockheed Martin in their facility in Littleton, Colorado. And it's part of a long heritage of space missions, going back to the Mars Reconnaissance Orbiter, Juno, which is an orbiter around Jupiter, the MAVEN spacecraft, which was also in orbit around Mars, and then OSIRIS-REx. Those are all kind of a similar bus, that is spacecraft, similar avionics, power systems, communication systems, and of course there are some custom science features. You can see quite prominently right here on what we call the science deck, this white nose cone with the orange back shell. That's the sample return capsule. That's the hardware that's going to come back to the surface of the Earth with the OSIRIS-REx samples from asteroid Bennu tucked inside of it. So you're going to see that capsule towards the end of the story today. There's a robotic arm, which is in its stow configuration right here. And this is what we call the bread box. This has the sample collector head attached inside of it to keep it clean during our processing and through the launch. And then this black blanketing is covering some bottles of high purity nitrogen gas, which was the strategy that we used to collect the sample. So this is me at the Lockheed Martin facility as we were going through our vibration testing. And then this is the team at the Kennedy Space Center in the Payload Hazardous Servicing Facility, the final days before we were getting ready to put the spacecraft on top of the rocket. And it's a really cool place to be because you can see in the background all the logos of the famous missions that have gone before us. Here's the Phoenix Mars lander, which was also led by the Lunar and Planetary Laboratory at the University of Arizona, Hubble Space Telescope, Mars Exploration Rovers, New Horizons mission to Jupiter, and on and on and on. You just get a sense of enormous history. All the planetary explorers that went before you went through the same facility on their journey to the solar system. Here's a better view of the sample collector in its now deployed configuration. So it's a robotic arm, about 3 meters in length. And then you can see bagged here to maintain that cleanliness is what we call the TAGSAM head, or the touch and go sample acquisition mechanism. The strategy, and you get a sense by looking at it, it kind of looks like an air filter, and it is an air filter, same strategy. You just push it down into the surface of the asteroid, open one of these bottles, which are exposed here, and like a leaf blower, just push the gravel and the dust into that filter, and then tuck it away into the return capsule, which you can see here, opened like a clamshell. And then the robotic arm can articulate that filter right into a capture ring, and then you sever the bolts and the tubes, and the arm stays on the spacecraft, and the entire filter with all the sample inside gets tucked inside the capsule. Here is our timeline. I like a couple things about this slide. First of all, we had a graphic artist on staff throughout the entire mission, and she did an amazing job. Her name's Heather Roper. She started as a student here at the University of Arizona, and we liked her work so much. She still works for us today, creating things for the OSIRIS-APEX mission. She works for the Arizona Space Institute, doing lots of graphics for proposals and other. Yes. Let's go back. So the timeline is we were selected for flight by the agency in 2011. We spent 5 years designing, building, testing, and then assembling the spacecraft with the launch vehicle. We launched on September 8th of 2016 out of Cape Canaveral. We had to come back to the Earth in 2017 for a gravity assist. Think about that orbit diagram where the plane of the asteroid's orbit is inclined 6 degrees relative to the Earth. We couldn't do that inclination plane change with our propulsion system. We needed to use the Earth's gravity. And you can see here is Australia in the background. We actually flew under the South Pole of the Earth and bent the trajectory of the spacecraft up for the rendezvous with the asteroid, which occurred in December of 2018. We spent all of 2019 mapping the surface in exquisite detail, desperately casting around for a safe sample site because the surface was much more rocky and rugged than we expected. And then in October of 2020, we sent the spacecraft down to contact the surface with the tag SAM, collect the sample, setting us up to depart in May of 2021 and culminating the flight program on September 24th of 2023 when that capsule landed safely on the Earth. And so now we're here in mid-2025. I've been showing this timeline for 15 years, and it's a little bit bittersweet to be in the last box here in the final year of our sample analysis program. Wrapping up, which for me has been a lifetime adventure to get out to this asteroid, collect material, and get it into our laboratories. These were the very first close-up views that we got of the asteroid when we got into proximity. We were doing our what we call preliminary survey phase, and really getting a sense of the challenge that was in front of us. We had designed the navigation system to sample an area about 50 meters in diameter, which is about 10% of the diameter of the asteroid, expecting that the majority of the surface would be smooth, sandy particles, and that was based on interpretation of radar data from the Arecibo Planetary Radio Telescope and the Goldstone radio telescopes, which showed a polarization ratio similar to fine particles or a low radar roughness surface, and also data from the Spitzer Space Telescope, which is an infrared telescope that allowed us to measure a property called thermal inertia, which measures how fast the surface heats up and cools off, and it heats up and cools off very quickly like fine particles tend to do. So we intuited and interpreted that information to mean small particles on the scale of a centimeter or so. And this thing's dominated by meter scale boulders and larger, the largest boulder being about 100 meters across. From a science perspective, though, it was good news in the early days. So we picked Bennu partly because of its orbit, actually largely because of its orbit. You can see being a near-Earth asteroid in that configuration allows us to launch, rendezvous, return back to our planet with relatively low energy as solar system exploration missions go. But there were a dozen or so objects that met those orbital criteria, and Bennu was selected because of its low reflectance, which we expected meant high carbon, because it's an astrobiology mission. I'm going to tell you some of the exciting results that we've got later on in the presentation. We think asteroids like Bennu, which date from the very dawn of our solar system, from 4.5 billion years ago, from the first population of planetesimals, those kinds of objects, those dark carbon-rich objects, delivered critical compounds to the inner solar system, including water, which makes up our oceans and our bodies and that of all life on Earth, the molecules in our atmosphere, and the organic building blocks that went ahead to assemble and become alive. And what I'm showing you here are some of the early spectroscopy data. This is in the near infrared, so we're starting at 2.2 microns, out beyond what we can see with our eyes, extending out to about 3.4 microns. And it's normalized, so we take the spectrum of the sun, we see it hits the asteroid, we normalize it, and so if there was no chemistry or nothing absorbing photons, this would just be a flat line at 1 all the way across the graph here. And you can see Bennu's pretty flat. It's the blue line here. And then at 2.7 microns, the signal plunges pretty dramatically, and then it rises back up And out here at 3.4 microns, you can see in some of the analog material, so these are meteorites that we thought Bennu might be similar to. There's features here at 3.4 microns, and you can see similar hints here. This was early days. There is, in fact, an absorption feature here. The 2.7 micron is due to the hydroxyl molecule. That's an oxygen bonded to hydrogen. Very exciting for us. It's water, not in the sense of liquid water or even ice on the surface of the asteroid, which wouldn't be stable in the inner solar system because it gets very hot, but water locked up in clay minerals. So it literally is OH structurally bound into minerals, and that's what we're seeing in the 2.7 micron feature. And then out of 3.4 micron, these are hydrocarbons, carbon bonded to oxygen, and also carbonates, carbon bonded to hydrogen for the hydrocarbons and carbon bonded to the oxygen for the carbonates. So hints of water, which we were very excited about, and also carbon-bearing materials, possibly organics and carbonate minerals. So we spent that year of 2018 investigating in the surface and improving the guidance accuracy on the spacecraft, and we got it down from 50 meters to about 5 meters. And we ended up with 4 potential sample sites named after birds that are native to Egypt in honor of Bennu, which is an Egyptian heron. And so down in the South Pole, we had the Sandpiper site, which is on the wall of a very large crater. And it was kind of this, what I called runway area right here. So this is the downslope direction where my cursor is going. And there's a large boulder right there, and it's kind of blocking. All these other rocks are tumbling down the crater wall, but this rock is shielding this one region. So we thought we might be able to get the spacecraft in there and collect material from this spot. At the equator, we had the Kingfisher, which was selected by our citizen scientists. We were working so hard to characterize the surface, we engaged citizen scientists through the CosmoQuest app or website, and they picked the Kingfisher, and it looked really good, except that the best part was this tiny little crater, which is about 1 meter across right there, and we just thought that was a little too tight. Also on the equator, we had the Osprey, which was one of the most distinctive craters on the surface. It looked pretty good, except for this giant boulder right here. The crater is about 20 meters in diameter. We called this 12 o'clock rock. You can kind of see why, right? It's sitting right there at 12 o'clock. And it was kind of really confounding us because the best spot to collect the sample was right off here around 3 o'clock, and we were worried about this object so close to us. And then finally, the winner of the campaign was the Nightingale site in the north, also about 20-meter diameter. It had another giant boulder on the eastern rim here. We'll take a look at this site in a little more detail. So here is the Nightingale, and again, this is real data. This is topographic data from the LiDAR overlaid with the imaging data from our Polycam. And you can see why we like this. If you look at the outer rim of the crater, you can see the large boulders, that pretty typical of the surface of Bennu. And then in the interior here, kind of the fine-grained material that we expected from all of that data interpretation. And then the really scary part was there was a few large boulders. These are meter scale boulders in this region, but it was this object over here that gave us lots of nightmares, and we would nickname this one Mount Doom. And you'll see why when it comes around, and it's got this really kind of classic angular peak that looks like it's right out of a Tolkien landscape. But everything about this looked great. It was accessible. It had fine-grained material. We actually ended up imaging the entire crater at about 3 millimeters per pixel. And the sample collector could pick up particles as big as about 2 centimeters guaranteed. So we could easily resolve the kinds of rocks that we would be able to collect. Despite the hazard, it had a fairly large area that looked safe for us. So we went for it. And it was in the northern part of the asteroid, I think the latitude about 54 degrees north. Here's that Mount Doom profile that kind of gave it the moniker. And we had to fly right over the top of Mount Doom and then drop down into the crater to collect the sample. Okay, so here is the moment. So we all worked out, thankfully. We got down to the surface of the asteroid. You can see the filter touching the asteroid's surface. And the basic idea was that the surface was going to be hard, and kind of like walking on the surface of the moon, and that we would just push it down onto the surface and we would pick up, the first couple centimeters or so. Now, that is not what happened. So we came in at a velocity of 10 centimeters per second, which is about the speed that I'm walking right now, kind of like a baby crawling, very, very gentle touch to it. And we waited 1 second to fire the gas because we wanted to make sure we were well seated on the surface. And then 6 seconds later, we had a 5-second collection window. We were still moving downward at 4 centimeters per second. So we had decelerated by 6 centimeters per second. That deceleration was entirely due to the gas coming out of the base of the collector. What that means is that there was no resistance whatsoever to the downward motion of the spacecraft from the asteroid surface itself. It basically responded like a fluid, and you kind of get a sense looking at the imagery here because the sample head is in shadow, and you can actually see it when it comes back out and lights up right there. So we ended up going about 17 seconds and penetrating about 50 centimeters into the subsurface of the asteroid, which was good news for sample collection, and also some really interesting science came out of it. Here's a different view. So that was the SAM cam looking straight down, and then here's the nav cam, which is looking off to the side. That was the shadow of the collector, and you can kind of get a sense of the enormously dynamic response of the asteroid surface relative to the scale. So you can still see the shadow of the robotic arm here. We're starting to back away. You can see there's this ridge. This is a crater wall that we're excavating from the action of TAAA. And then you can see there's kind of this X profile of the debris. This area is where the backaway thruster is hitting and kind of scouring the material away. And now in the upper right corner, you're going to get a view of the undisturbed asteroid surface. And you're going to see lots and lots of very large particles that are streaming across our field of view. Some of them are very close to our spacecraft right there. It was an incredibly dynamic, unexpected event from the contact with the asteroid. And when we had tested this thing in reduced gravity aircraft, NASA's Vomit Comet, famous gravity testing facility, we never dug a hole bigger than the collector itself. It was always about 30 centimeters in diameter. But after I saw those images in October of 2020, I said, we have to go back and we have to characterize the surface. We can't leave without knowing what the surface looks like after this dynamic event. And that wasn't in the baseline plan because we didn't expect to particularly move much material. And we thought it'd be really hard to see the actual location where we contacted. But here, this blinking set of images shows you what the difference looked like. So this is the pre-contact image. The X marks the spot. You can notice a couple things. The surface got darker. The grains were smaller. Average grain size decreased. And the red circle is indicating one of those meter scale boulders that I pointed out in the 3D model that got kicked directly by the thruster, and we launched it 12 meters out of the crater over to this area right here. And we ended up excavating a crater about 8 meters in diameter. It's an elliptical crater, so 25 feet across, moved an enormous amount of material as a result of the sample collection event. And we've used this information to characterize the bulk properties. It's basically cohesionless. That is, there's no force between the different particles. That's why it's acting like a fluid. And the density at this site was incredibly low. The bulk density of the surface was 500 kilograms per cubic meter. Your average rock is 3,000 kilograms per cubic meter, and ice is 1,000 kilograms per cubic meter. So the density at the surface of the asteroid was half that of water ice. And we use that information. A lot of my team members, especially those at Johns Hopkins Applied Physics Laboratory, went on to participate in the DART mission, which impacted a moon around another asteroid. And all of this information and modeling they applied to understand the nature of that impact. So it was really fed forward. So we had to reconstruct what that event looked like. So here is an artist's conception of the sampling event, processing all of that information from the spacecraft, making contact, sinking down into the subsurface of the asteroid, firing the gas bottle. An enormous amount of material is liberated by that dynamic event. Then the thrusters fire, reorient and mobilize the material in a variety of different directions. We're completely buried in material at this point, frighteningly so, right? I mean, this is a $400 million spacecraft on a $1 billion NASA mission. And every time I watch this video, I can't believe we survived the event. It was so unexpected, but it was good news. First of all, the spacecraft is tough. It came away without any sign of degradation. Notice that the solar arrays are pushed all the way back. The active area is far away from the surface. There was no change in power production. We have radiators that keep the electronics cool by emitting infrared photons into space. They were working fine. The thrusters didn't have any sign of debris inside of them. So the spacecraft was unaffected by the entire event and very healthy in operating condition. So we stowed the sample about a week later, estimating that we had particles ranging from submicrons to about 3 centimeters. And based on the spectroscopy, some of which I showed you, we expected to have hydrated phyllosilicates. Those are the clay minerals that have water in their crystal structures. Carbonates from that 3.4 micron feature. An iron oxide called magnetite. Sulfide minerals, which we didn't see, but we expected just by studying meteorites, and abundant organic material. So this is what we were predicting would be in the sample when we came home. In May of 2021, so we had to wait 7 months. Notice that the flyby to get the post-sampling data was in April of 2021. So about a month later, we fired the thrusters, leaving Bennu in our rearview mirror, saying farewell to our cosmic friend with the scientific treasure in hand. And then in September of 2023, so about 2.5-year journey back home, the spacecraft approached the vicinity of the Earth, released the capsule from about 60,000 kilometers out, targeting a 50-kilometer patch in the Utah desert, the Utah Test and Training Range. So here's actual footage from the spacecraft as we release the capsule. This is the limb of the Earth here. The sun is just off of the field of view, and you can see the capsule. It's a dumb capsule. It has no guidance system whatever. We do spin it. You can get a sense that it's rotating. So kind of like throwing that perfect touchdown pass into the end zone, right? So you spin it to stabilize its flight through the atmosphere. Just to give you a little bit of setting here, so I was in the Utah desert. I was on the field team to get out and recover the capsule. And I had to get up about 2 o'clock in the morning, because that's when we did the spacecraft command conference, giving the go to release the capsule. And because we had to make sure we were in a safe configuration, we weren't going to land in Salt Lake City or something like that. So there was that little bit of tension, like, okay, let's get the go. And then we had to power up the batteries. They had been passivated, so they didn't drain. We hadn't talked to the batteries in 7 years of flight. They came online, so everything looked pretty good. And then a couple hours later, I'm in a helicopter flying out to the Utah desert. We're working in partnership with our colleagues in the Department of Defense. Both the Air Force and the Army are active out at the Utah Test and Training Range. And there's an Air Force officer sitting in the seat in front of me. And they say, okay, capsule has been spotted, airspace over California. 2 seconds later, it's over Utah airspace. So we crossed the entire state of California in 2 seconds. We hit the top of the atmosphere at 12.4 kilometers a second, or about 28,000 miles per hour. And then we're in Utah airspace, and she calls out crossing 100,000 meters. And I'm like, okay, that's when the drogue parachute is supposed to deploy. So at that point, we've dropped most of our velocity through friction heating with the atmosphere. And she says, capsule spotted. And I'm like, and the parachute? And she's like, no shoot. And I'm like, oh man. I'm thinking about a mission 20 years ago called the Genesis mission, which was a solar wind collector built by Lockheed Martin, and the parachute didn't deploy because they installed the release switch backwards. And I know we didn't do that because we tested it many, many times in flight at the assembly level, which is something the Genesis mission didn't do. 50,000 kilometers, no shoot. 40, no shoot. 30, 20. Finally, at 10,000 kilometers, she calls main chute spotted. And I was like, what? That's not right. The drogue was supposed to come out, and the main chute was supposed to come out right here at the final. But I was like, I don't care. We'll figure out what happened later. But this was a beautiful sight to see this capsule coming in. This was captured by a camera on the ground that the Air Force operated. And you can see it just goes right past that ridge, so we don't actually see the touchdown, but you'll watch the parachute deflate right there. So we know it's on the ground. And we're on our way out. This is what we saw from the helicopters on the approach. Beautiful black and charred capsule, right? Remember how clean it looked on the spacecraft, the white heat shield with the orange back shell. This blackened debris is from that fiery passage through the atmosphere. Main chute right next to it, drogue chute right on the other side of it as well. Turns out what happened was the switch was in, but the circuit was backwards. So there was two things that had to happen. The first signal was when the capsule released through 3 Gs of acceleration. So it pushed up to 30 Gs. It was kind of a piston. And then when it got below 3 Gs, that relaxed, and it sent a signal that was supposed to fire a mortar and release the drogue parachute. And then a timer was going to go, and then a few minutes later, the second signal cut the cable and the main chute pulled out. But that was backwards. So the first signal cut the cable that was holding the main chute in, and it was still inside the package, and there was no release because the mortar hadn't fired. And then the timer went, and fortunately, we had a pressure transducer that just said, if you get to this depth of the atmosphere and the thing hasn't fired, just blow the whole system. And that's what happened. And the second signal fired the mortar, the drogue, the main chute all came out within milliseconds of each other. And we also put a ton of margin on that harness, so we're able to arrest our velocity and safely bring that capsule home. And then I got to go out into the field and be on the environmental sampling team. So keeping the sample pristine is a big part of our job here. And I can't tell you what it was like to see this thing in the desert after all these years of designing and planning and operating and implementing and stressing over this entire event. It was there. It looked perfect, right on its nose cone like a gymnast that just stuck the landing. And I tell you, it was like seeing an old friend, right? Somebody I hadn't seen for 7 years that had been traveling the solar system and was now back on Earth with this scientific treasure. So we quickly packaged it up. We got rid of the heat shield, the back shell, the batteries, and the avionics, none of the stuff that we needed anymore, and just what we call the science canister, which is like the treasure box that has the tag SAM inside of it with the sample inside of that. Here we are delivering it into the special curation laboratory at NASA Johnson Space Center. We're opening up that canister, the treasure box, and you can see tag SAM for the first time right there since we stowed it back in 2020. And there's your happy principal investigator celebrating the first time I got to set my eyes on asteroid dust collected from Bennu. So this is the tag SAM. You can see there's the tube that delivered the gas, and it has been severed, kind of like a guillotine, cut that off. There's black dust all over the top of it. One thing we did see is that the capsule was definitely nutating after that drogue failed to deploy, because that's what the drogue is supposed to stabilize, and may have even tumbled. So we may have been going end over end in the atmosphere before that main chute came out. So the dust was going everywhere. And then there is a little bit of fine grain dust right here. And it's just right on the edge of the canister lid. And then this is a second ring of larger particles, and it's braided because there's a braided metal seal that goes along there. And this was because as soon as we got out into the field, we put it on nitrogen purge to prevent the atmosphere from getting exposure to the sample. And it pushed a lot of this dust to the outer rim. And this was great news because this meant on day 2, we swept up some material and we got it into the laboratory, and we started the sample analysis program to get a sense of what did we bring back. What we brought back was twice the mass that we promised. So the mission was required to bring back 60 grams of sample. We brought back 121.6 grams. These tick marks down here are 1 centimeter. Here's the whopper. We call you'll see, I won't tell you the nickname yet, but this is the largest one. It's about 3.5 centimeters. Lots and lots of centimeter scale particles throughout, tons of fine dust. Just a beautiful collection to get into the laboratories and begin our sample analysis investigation, the primary science campaign of the program. And so I want to give you a little bit of sense of the nature of the material that we collected. And we're going to first go back to the asteroid surface and take a good look at the different kinds of boulders that we see on the surface. So note the scale bar here is 10 meters, so almost 30 feet across. And you can see these large black boulders that are pretty characteristic of the biggest objects on the surface of the asteroid. And we call these hummocky boulders. Hummocky meaning they kind of have a cauliflower-like texture to them. This one is a named feature. Actually, all these are named features approved by the International Astronomical Union. And they're all named after mythological birds, except for the gargoyle. I insisted this one be called the gargoyle. I'm like, a gargoyle is kind of like a bird, right? And it's because it's sitting on this pedestal. It's a really fascinating structure. It's actually layered. It looks like sedimentary layers. And I have a student who wrote a paper on this a year ago or so. And these are the darkest objects on the asteroid surface. And they have this really rough texture, and there's lots of clasts that you can see kind of embedded. This one is like a little diving board. You can see the shadow right here. And it looks like a mud flow kind of structure. And then when we look at the samples, now we're looking at the centimeter scale here, we have hummocky textures in the sample. So we have a lot of these rocks are very similar, reminiscent of the much larger meter scale features that we were seeing on the surface of the asteroid. And I was looking at it, I was like, there's no way that you could have something at a meter scale kind of reflected down at the centimeter scale. You're moving through a couple orders of magnitude. And then we take a look at the other kinds of boulders that are on the surface. We call these the angular boulders. And you can see they have very well-defined angles, very sharp faces. They're fracturing in a very linear fashion. Sometimes they're exfoliating, like you can see right here. And sure enough, a different population of the rocks that we brought back, again at the centimeter scale, have this very angular kind of structure to them as well. Sharp geometric features, flat linear faces, fracturing along clearly defined fault lines in the sample. So I was like, well, that's really interesting. We got hummocky boulders, we got angular boulders, we got hummocky particles, we got angular particles. So there is a fractal nature to the way these rocks are breaking down on the surface of the asteroid. And then there's these rare types of boulders that show these bright white veins that are shot through them. So here we've got a 1 meter scale bar. It's so bright that it's saturated the pixels on the camera. So we can't actually calculate the albedo. We can only get a minimum reflectance on it, and it's minimum about 30% versus the boulders, which are about 4 to 4.5%. There's another vein. You can kind of just see it off to the side here. We have other shots of this boulder from this angle, and there's another vein running through it right there. And when we take a look at the spectroscopy, now we're focusing on that 3.4 micron feature that I pointed out to you earlier. Here's Bennu, and then here are known carbon-bearing minerals. This is calcite, very common carbonate mineral. Here in Tucson, we have hard water coming out of our faucets. It makes that white, crusty salt stuff that clogs up your shower head. That's calcite. So we see carbonate minerals. That means you had not only water, but you had soda water, you had carbonated water, and you had calcium in that water. And when the water evaporated away, it deposited calcium carbonate. This is siderite, which is an iron-bearing carbonate. We have magnesite, which is a magnesium-bearing carbonate. And then we have brunerite and dolomites, which are mixtures of iron, calcium, and magnesium, and also manganese. So we saw a wide range of different carbonate minerals on the surface, and they look like these bright white features. And sure enough, if we take a look at that biggest particle, this is the Whopper, and here I stretch it just to get a sense of these clearly defined areas. We ended up calling this the heart of Bennu, because you can see the shape that it has is very heart-like. And, you know, Pluto's got a heart, so now Bennu does too. Although, you know, I like to say we stole Bennu's heart and brought it back to the Earth. But let's take a look at that image processing trick again. So all I did was go into Photoshop and make the following changes, hue minus 25, saturation plus 90, and you get these really beautiful blue hues associated with the structures, and then they're rimmed by kind of much more reddish material. And it was like, this is something different, and I think it's related to those veins that we saw on the surface of the asteroid. And it also made it pretty easy to find more of this material, because we had beautiful imaging from inside those curation cabinets. And if I just did that same stretch, you could see, there's other occurrences of the same material sprinkled throughout the collection. So we have a lot of it here. We actually have this stone here at the University of Arizona, and we're studying this right now to understand its nature. So what are we looking at? Well, let's go into the electron microscopes over in the Kuiper Space Sciences building, which is across the street on the other side of the planetarium. We have a beautiful analytical facility with all kinds of electron microscopes and ion microprobes. And so we were able to get a pretty good sense of what we're looking at. And yes, most of the material is water-bearing clay minerals, and you can get a real sense of the nature. Now we're down at the micron scale. This scale bar is 2.5 microns. So I've taken you from a 500-meter asteroid to tens of meter scale boulders, centimeter particles, now down to micron-sized mineral grains. And this is what most of the material looks like. Clay minerals, you may be familiar with one called asbestos. Asbestos was used, I think, in the 1950s and 60s as fireproof insulation because it's a rock. It's not going to burn. But it also made these little fibers, which were hazardous for people to breathe in and could cause all kinds of health issues. This is what we're dealing with here. This mineral called serpentine, because it's kind of got that snake-like texture to it. We also see lots of these rosettes, which are a different clay mineral called saponite. And it's about 70 to 80% of the volume of the asteroid material are these hydrated clay, magnesium, silicate, hydroxyl-bearing clay minerals. We have lots of carbon. Here's the calcite, this thing that we saw, the mineral that we saw in the spectra in those bright white veins. It does fill veins, and it's got these beautiful, well-defined crystals. Looks like it was growing into a void. We're famous in Tucson for our Gem and Mineral show. Many of you have probably been to some of the dealer rooms, and you get these beautiful crystals. Those are all growing from hydrothermal systems where you have a void space that the crystals can grow without any constraint on their volume. And that's what we're seeing all through the asteroid sample. And then we also have these dark carbon veins that are organic rich material. So this is carbon bonded to oxygen. This is carbon bonded to nitrogen and hydrogen, a little bit of oxygen and a little bit of sulfur in there as well. So on the bulk composition of the asteroid, we're seeing between 4.4 to 4.7% by weight of carbon. So it is exactly the kind of sample that we wanted. Loaded in water, about 9 to 10% by weight water, about 5%, a little less by weight carbon. And these are the kinds of objects that brought the carbon that's in our bodies today, the water that's in our oceans, the water that we drink to stay alive. All of that at one point in time was in these clay minerals, and these were delivered to the early surface of the Earth 4.5 billion years ago. Lots of beautiful minerals. I mean, we could just spend hours, and we do, just going down on the electron microscope and zooming around on the different particles. I have graduate students, and I remind them every day how lucky they are to be in graduate school right now at this university studying these samples that we spent decades planning to bring back. Here's an example of the iron oxide, the magnetite. We call this the framboidal form after the French word for raspberry, framboise, right? They look like little raspberries. And if you can zoom in and take a close look, they're actually like dodecahedrons. They're little crystal forms of magnetites that have grown together in these little pockets. Gorgeous sulfide minerals. I wrote my PhD thesis on iron sulfides in the early solar system, so it's great to see. They have this beautiful hexagonal kind of structure and this banded form to them. And then just in February, we published the first major results, and we were excited to make the cover. This is a big deal in science if you make the cover of Nature. And these are sodium carbonates, which we didn't predict from the spectroscopy here. And you can see they're just these beautiful bladed crystals growing into these void forms. So now we've got calcium carbonates, we've got magnesium carbonates, we've got iron, manganese-rich carbonates, sodium carbonates, and it turns out we have sodium chlorides, we have sodium fluorides. So it turns out that those bright material that we see on the surface of the asteroid are literally salts, right? I called it salt and pepper texture when I was first characterizing the surface back in 2018, and I had no idea that I was actually looking at salt crystals that were there. And this is an incredibly exciting result for us. One of the first ones that we got here in the laboratory at Arizona was this little guy right here. He's about 1 millimeter across, stood out very clearly because it's got bright white material encrusting its surface. This fragment actually broke off from this area here, and you could, so this was in the interior of the stone. This is the optical image. This is an electron image over here. We're going to go ahead and zoom in on a couple areas. This is zoomed in right here. My son, a teenager, was in the lab when we were collecting the data, and he said this looks like alligator skin, and that's kind of the name that we've given it. It shows up very well in the electron microscope. And then down here, you can get a sense of this region, and we're looking at a thickness of about 20 microns right here. And this piece is a flake that broke off from this region right here. And this material looks like average Bennu. These are your clays. You have some of the oxides and sulfides, which we can spot really easily because they have such distinctive crystal forms. So this is a late stage deposition. And I thought for sure when I got this grain that this was going to be the carbonates, because that's what we saw with the spectrometers, and that's what we were expecting the dominant salty minerals to be. But these turned out to be phosphates, which is very unusual. Not only that, but they're magnesium and sodium-rich phosphates. And when typical rocks on Earth, if they have phosphate minerals, they're calcium phosphates. Things that make up our teeth and our bones are calcium phosphates. Life uses phosphate all over the place. It makes up our cell membranes. Those are called phospholipids. It's the primary energy molecule. It's called adenosine triphosphate. So the mitochondria and all your cells are making ATP molecules and sending them to all the places you need. I'm up here on stage moving my arms around and talking to you. All of that is because I'm burning triphosphates inside my body so that I can do all these things. And this salt is all over the place in the sample. And that particle that I showed you that we have here in Arizona, all of that material is phosphate. And what's really interesting is the blue part is ammonium rich. So this is ammonia in this phase. It's not a crystal, it's completely amorphous. It has no crystal structure to it, which means it deposited very quickly. And then the red areas that are rimming it are where the sodium is concentrated. And sodium tends to make things redder. So we're seeing these various phosphates all throughout the sample. And what we've pieced together is, okay, the dominant mineralogy are hydrated clay minerals. We got all these salts, we got oxides and sulfides. We see this mineral assemblage right here on Earth. This isn't a surprise. This is a rock called a serpentinite. And serpentinites form when seawater hits the mantle of the Earth, primarily reacting with a mineral called olivine, which is the most abundant silicate mineral in our planet. And it makes these environments called the white smokers. These are low temperature, relatively speaking, hydrothermal vents that are found at the base of the ocean. You can see all the crusty white salt minerals. These are all your carbonates that are being deposited throughout here. And now this is incredibly exciting. So we have rocks from a hydrothermal vent system that was in the early solar system. And we think that this might be a key location for the origin of life on Earth. When these were first discovered, that's what immediately people were saying, aha, because there's all kinds of life living down here. There's macro animals like this crab that you can see right here. There's worms. There's all kinds of cool bacteria and archaea. We call them extremophiles. They don't need photosynthesis. They actually eat the rocks. They're called chemoautotrophs. And we can't really study these sites on Earth for origin of life investigations because there's life all over the thing. And so you're like, well, I can't tell you if these molecules came from the hydrothermal vent because probably that bug died and dumped all those proteins and amino acids in there. But now we have something from the early solar system from an object that didn't have the origin of life, at least as far as we can tell, although I'm going to tease you a little bit right at the end. And so we can study an abiotic hydrothermal vent system from the dawn of the solar system to understand the organic molecular evolution and the kinds of compounds that could have been delivered to the early Earth. And this isn't the only place in the solar system where we think this is happening. There's a very famous moon around Saturn called Enceladus. This is an incredibly famous image from the Cassini orbiter. As it passed the south pole of Enceladus, it saw these geysers erupting from what are called the tiger stripes or fractures in the crust, the icy crust of this moon. And we think that what's going on here is you have an icy shell and a rocky interior, and in between those two, you have an ocean. This is what we call an ocean world. And at the rock-ocean interface, you probably have serpentinization occurring because the dominant rock mineral is going to be that olivine. The water is going to be salty. And when salt water hits olivine, you make serpentine. That's why it's called a serpentinite. And it's an exothermic reaction, so it releases energy or heat, and that's what drives those hydrothermal systems at the bottom of the ocean. The white smokers, there's a different class called the black smoker, which is actually magmatic heating, and we don't think that we're looking at a system like that. So that gets to now astrobiology. I started the Arizona Astrobiology Center about 2 years ago now, and that really is my transition from the spacecraft mission to the science that I'm pursuing by studying these samples and gathering like-minded researchers from across the campus and from across the world. So let's just take a step back and review what we think is the kind of the dominant paradigm for the origin of life on Earth. And it really is this arrow. You start down here with inanimate matter, which you would agree is not alive, and then through some chemical evolution and something else maybe, life arises out of here. And you start out with the kind of basic molecules which we see all over the universe, because hydrogen is the most abundant baryonic matter, and it dominates like 90+% of all the matter that makes stars and planets is hydrogen. And then you have the next most abundant reactive molecules, carbon, nitrogen, and oxygen. So you can make oxygen hydride, we call that water. Nitrogen hydride, we call that ammonia. Carbon hydride, we call that methane. You can have hydrogen sulfide, and you have phosphates, or you can have phosphides as well. And so those go through some chemistry, and you make things like nucleobases. These are the letters of genetic code. You make amino acids. These are the building blocks of proteins. And you make lipids, which are cell membranes, which encapsulate all of this so that you can have something that's alive. And then these things start to polymerize. And your nucleobases, by adding phosphate, which is a component of DNA and RNA, as well as the ribose or a deoxyribose sugar, to make your nucleic acid. This is your genes, where the genetic information is stored in life. Your amino acids make chains and become proteins. And your lipids bond together just through their hydrophobic similarity, and they make membranes. And then somehow that becomes a cell that's alive. And we have no idea how this happens right now, but we're looking at this process through the lens of the asteroid sample. And we know you had ices in the early solar system. You had water ice, methane ice, ammonia ice, et cetera. And we want to know, did you make even this first step? Did you get to the nucleobases or the amino acids? So let's take a look at our nucleic acids. So here are the letters of the genetic code. There's 4 in DNA. It shares 3 of those with RNA, and then 1 gets swapped out. And if there's a green box around the compound, it means we've detected it in the asteroid sample. So all 5 letters of the genetic code are in asteroid Bennu. The backbone of DNA and RNA is a sugar phosphate, where you have ribose, found in the asteroid, connected to phosphate, found in the asteroid. So we have the building blocks to make DNA in this asteroid sample. What about the proteins? We have 20 amino acids that are commonly used to make all the proteins on Earth. All life uses these 20 amino acids. The genetic code takes the nucleobases, the sequence in your gene, which is a recipe for these amino acids to make whatever protein you need. And proteins do all the stuff in your body. They're the workhorses. They catalyze your metabolic reactions. They provide structural support, and so on and so on. They make your muscles. If you take protein supplements, you'll see these 20 amino acids that are listed on there and how many of them. So out of the 20, we now have 15 of them so far detected in the asteroid sample. So we're missing 5, and we're desperately looking for them. Some of them are just unstable. Some of them could be formed from these other ones through metabolic processes. And then we get to the idea of lipid membranes, or the cell wall. And one of the things that stands out in the asteroid sample are these, we're calling them organic nanoglobules. So here, this is a transmission electron microscope image. So now we're down at the micron scale. And a micron is 1/1,000,000th of a meter. Take a meter, divide it into 1,000,000 parts, and that's a micron. And these looked really compelling to us. So here is just the electron image. So this is a transmission electron microscope, so the electrons are going through the sample. And then we can also excite X-rays by that process, and we can tell what the chemical elements are there. And so this is a 3-color image with red mapping to carbon, green mapping to silicon, and blue mapping to iron. And the boundary of this nanoglobule is organic carbon. And it's aromatic, which means it's in ring molecules because it's fluorescent. That's how we find them. We find them in a fluorescent microscope. This is really compelling to me. I particularly love this picture because there's 2 nanoglobules here, and they're either merging or they're dividing, right? And we don't know which way that reaction was going there, but that's starting to look a lot like a cell membrane. We don't have phosphorus here, so it's not a phospholipid, which would have been maybe a Nobel Prize if we had actually found that. But this is a key step in the origin of life. This is encapsulation, right? This is a boundary that separates a system from its environment, and that's a hallmark of all life. For us, it's our skin. For bacteria, it's their cell walls, and so on. And what's even more interesting is there's all these little fibers in here, and these are your clays. It's just like taking just strands of those serpentines and locking them in here. Some of them look like they have fluid inside of them, so they actually trapped some of the fluid that was floating around on the asteroid. And we're trying to figure out how to characterize them because every time we go and look, they pop on the electron beam. So we can't characterize that fluid. We're going to try to freeze it. We're building a cryo stage for the electron microscope, see if we can freeze it and characterize what's in there. But there's also organic material associated with the clays, and you can see the carbon signals showing up in here. So there's something really important going on to give us some clue to the origin of life. So let's just go back to our basic diagram here and say, well, we definitely have water in the clay minerals. We have ammonia. Actually, we did detect ammonia. That was one of the big discoveries we published in February in a companion paper to the salts in Nature. The organics was in Nature Astronomy. We have hydrocarbons. We don't have methane, but we have lots of CH compounds, more advanced ones. We don't have the hydrogen sulfide. That's turned into the iron sulfides. And we have the phosphate all over the place. We have all the prebiotic molecules, the nucleobases, the amino acids, and we might even have something that's like a membrane. What we don't have yet is we don't have a protein. That would be linking multiple amino acids together into a chain. We call that a peptide. No sign of that yet, but we're still looking. No sign that you took the phosphate, the ribose, and the nucleobases and you made what's called a nucleic acid, which would be those three together. And then if you start to link those up, you get genetic material. And nothing that we could call a cell that would be a definitive life form yet. But a lot of really interesting information coming from this asteroid indicating not only did the Earth get this material from these carbonaceous asteroids, but Venus would have gotten all of this, Mars would have gotten it, the moons of Jupiter, the moons of Saturn, Uranus, Neptune, all these places in the solar system got the same kit. And then the question is, why did the origin of life occur on Earth? And did it occur on Mars? Did it occur on Venus? Did it occur on these icy bodies of the outer solar system? That's what astrobiology is all about, understanding this process. How do you go from something that's not alive to something that is alive? Why did that happen on Earth? And did that happen anywhere else in our solar system? And of course, now we have James Webb Space Telescope out there looking at atmospheres of exoplanets, teasing us with ideas that maybe they found signs of life in those objects as well. And I just want to end with, we found all these cool molecules, and I highlight them, but we found like 10,000 other molecules as well that are not these. So these are the ones we get excited about because they're used by life, but there's lots of other organic chemistry going on here. So it was clearly, we think, an abiotic process. And the question is, how do you filter? How do you take the 10,000 that are on this asteroid and pick the 20 to 30 that you need to make all the biomolecules on Earth? And that's the mystery of the origin of life. Thank you for your attention.
Okay, we will take questions. Do we want to take them in the room first, Terry? Okay, so we have one. I need to run the microphone around, so it'll take a little bit of time.
Fantastic presentation. During sample collection, how far were Bennu and the spacecraft from Earth?
We were on the opposite side of the sun, so it was an 18-minute one-way light time between the Earth and the spacecraft. Yeah, so it was all autonomous. That's why the spacecraft had to be autonomous.
Okay, we're on our way to another question here.
You pointed to a lot of evidence that indicates hydrothermal events in a bulk water. But where would Bennu get that setting? Well, you pointed to Enceladus and you pointed to deep ocean on the Earth, but I don't think that Bennu came from those settings.
Great question.
Are you thinking that Ceres or Vesta or who knows what used to have ocean water? Or how does this work?
Ceres might have ocean water today, so that's still, we consider it a potential ocean world. We see salts, for example, those sodium carbonates. We see those on the surface of the asteroid in relatively recent impact craters. Bennu is a fragment of a much larger world. That's clear. It's a pile of rubble. And when we do the dynamical evolution of the asteroid and we integrate it back, it definitely came through the inner edge of the main belt, through the new 6 resonance. You guys know what that is. It's a dynamical resonance with Saturn, actually. It sculpts the inner edge of the main belt. And we can trace it back to one of two, what we call asteroid families. So there's these collections of asteroids that share very similar orbital characteristics and similar spectral and reflectance properties. And they look like they all came from a single point. So what happened was you had an object at least 100 kilometers in diameter, maybe up to 500 kilometers in diameter. And it was shattered in a catastrophic disruption anywhere between 1 billion and 2 billion years ago. And it made thousands and thousands of objects like Bennu. There's another asteroid called Ryugu, which our friends in Japan visited with the Hayabusa 2 mission. they look like they're also from the same collisional environment. The fact that we have so much ammonia in the sample means that the original parent had to accrete pretty far out in the protoplanetary disk, because ammonia ice is stable at much lower temperatures even than water ice. And so ammonia, the condensation front for ammonia in the protoplanetary disk would have been about 10 astronomical units. So if the parent body didn't accrete out there, at least the ices that ended up in the parent body had to condense at 10 astronomical units. So we put together this nice dynamical story where you accreted the object in the outer solar system, 100 to 500 kilometers in diameter. Enceladus is about 500 kilometers, to give you a reference point. And there was a lot of radioactivity in the early solar system. We had extinct radioisotopes, particularly aluminum-26, also iron-60, plus you had uranium and thorium and potassium, the ones that are still heating the interior of the Earth today. That would have melted the ice and drove that hydrothermal system. And that hydrothermal system may have persisted for tens of millions of years, so pretty quickly. And then the system would have died down. There was dynamical scattering because the giant planets migrated around, and it got emplaced in the inner asteroid belt. And it hung around there for probably 3 billion years, and then was shattered in this catastrophic disruption. Bennu formed as maybe a larger object. We think Bennu might have gone through a collisional cascade and had multiple disruption events. And because it's so small, it gets pushed around by something called the Yarkovsky effect, and that pushes it into that new 6 resonance. It probably entered near Earth space, we estimate 1.75 million years ago, and that's turning out to be correct with cosmic ray exposure ages that we're seeing with the asteroid sample today. And its ultimate fate is to either collide with the Earth or more likely fall into the sun.
Yeah, I got a question regarding okay, so the so if Bennu is like a collection of a bunch of like dust and rocks or whatever, so if it were to impact Earth or like Venus, would the gravity of the larger planet make this thing stretch out into a bunch of
Yeah,
like a streamer?
If you remember Shoemaker Levy 9,
That's
when the
what I was
gravity, yeah, it would definitely distort if it got deep into the Earth's gravity field. And one of my colleagues, Bill Botke's done simulations, and it could pull it out into like a cigar-shaped object. It'll snap back when it gets out of Earth's gravity well, because that's kind of the equilibrium shape that it likes to take. And a fun future event is the spacecraft is still in outer space, right? We dropped the capsule off, but the vehicle's still out there. And it's on its way to another near-Earth asteroid called Apophis, which is going to do a close approach to the Earth on April 13th, 2029. It's a 300-meter object, so similar in scale to Bennu, and it's going to come within 30,000 kilometers of the surface of the Earth. You'll be able to see it with the naked eye in Eastern Europe and Africa during that event. So we think there's going to be a lot of public interest in this. And OSIRIS-REx has now been rebranded OSIRIS-APEX for the Apophis Explorer. And one of the key objectives of that new mission, which is going to go into orbit around Apophis, unfortunately right after the close approach, is to see exactly that. What is the tidal forces when it goes deep into the Earth's gravity well? What does it do to a rubble pile asteroid? It's not going to get close enough to disrupt Apophis, but we think it might trigger landslides and mass movement. It'll definitely torque it and change its rotation state. And APEX is going to go and investigate that.
So what percentage of Bennu is made up of all of the things outlined in green in your molecules?
So it's about 5%, a little less than 5% by weight carbon, and that's split between about 10% in the carbonates, 90% in the organic material. And a lot of the organic material is in the macro material, those like nanoglobules and those veins that I showed you. So of the soluble organics, which these compounds fall into, they're going to be about 10% of the organic carbon. So 10%, I have to do all the math, like less than 1% or so of the asteroid.
You were showing earlier that there were some rocks that had shown, or the clays that had started to streak. Is that driven from the original formation from these hydrothermal vents, or is this part of the process of sublimation as Bennu moved into the solar system and these ammonia ices and potentially water ices evaporated away and forming those geological
Yeah, that's a
features?
good question. I think the ices were melted in the early days, right? And then they went on to react to form the clay minerals. And it's a good question. What happened to the majority of the liquid? We do have some of it trapped in some of those minerals. There's a student who's got a paper that's been studying that. I think at least with the catastrophic disruption that would have occurred in the main belt on the order of 1 billion years ago, probably the ice would have sublimated away. And when we first were picking the asteroid, it's a spectral type called B type, and because it's kind of blue. And the other things that are B types we call them main belt comets or active asteroids. They do look like they have some pockets of ice that get exposed, and you get bursts of cometary activity, even though they're in an orbit that very much looks like a standard main belt asteroid. So it could have sublimated during that event. I don't think any ice would have made it in the surface of Bennu, even during its formation, but maybe in the interior, there could still be some in there. That's an unknown.
And a more humorous note. So given how diffuse or, fluffy that Bennu is, if a person were to actually try to step on it, how far up to their shoulders would they potentially sink?
Depends on how big your snowshoes are, right? Yeah, so that's a good question.
Now that we have hindsight, how close was OSIRIS-REx to being damaged or possibly taken out by the plume?
By the tag event?
Yeah.
Well, I would say we built it tough. We built it full of redundancy. It had timers to back away. So, we said 99.9% chance of success. I'm going to stand by that.
Do we have another question?
Online? Anything online?
Jim, do you want to do the Zoom
Can I see online
questions?
questions?
Yeah, you guys done in the room?
Looks like.
All right.
Maybe I can see.
I think we're finished in the room for now, Jim, if you want to go ahead.
Okay, from our members on Zoom, Tom O'Keefe asked, the angular boulders look like rock. The hummocky boulders look like maybe they're made of clay.
Everything's made of clay. The angular and the hummocky are all, in fact, we're trying to figure out what the difference is between the two. Why is one angular? I could say the hummocky seems like it's more clastic. It has distinct fragments still embedded inside of it, and the angular looks really homogeneous. I think it might be a pressure effect, like the angular might have formed at a higher pressure and got a more uniform grain size. And things made of clay are rocks. In geology, we still call them rocks. So we're not seeing a huge difference mineralogically between the hummocky and the angular, but it's texturally that we really see the difference right now.
All right, and Tom also asked, this one's a long one, so I'm going to read the whole thing and then I can go back to it if you don't catch it all.
Yep.
He says, regarding the crystals, did they form in situ on Bennu, formed by evaporation of the water? Was there some kind of water activity on the asteroid to form the crystals, or did the calcium and water arrive as the asteroid formed?
Yeah, great question. They formed on Bennu's parent asteroid. So Bennu is a fragment of a much larger body that had this hydrothermal system on it. And the calcites would be the first things, and they're probably precipitates. So as the solution is flowing, the calcite would form. But as you get to the phosphates, and I mentioned the chlorides and the fluorides, those look like evaporites. And if you look at the paper in Nature from February, you'll see we have a really nice sequence of where you transition from precipitation to evaporation. And so I think it's a combination of both. And we have a huge suite of minerals that are very characteristic of like alkaline lake environments on Earth. So formed on Bennu's parent body very early in the solar system, 4.5 billion years ago, through a combination of precipitation and then evaporation as the fluid dried away.
Okay, another one from Savan. Are the molecules racemic or racemic, or is there an anatomic preference as on Earth? I probably butchered
Molecules racemic, or is there an antiomeric preference? Great question. So when we talk about amino acids that make up proteins, the amino acids are, they have mirror versions of each other. There's a left-handed version and a right-handed version. And life, when it makes proteins, uses all the left-handed version of the amino acid. The amino acids on Bennu are racemic. They have equal amounts of left-handed and right-handed compounds, which you would expect from an abiotic chemistry process, not a biologic process. That said, Even if you take a collection of L amino acids, the left-handed versions, and you just leave them not in a biologic system, they will racemize. Some of them will start to flip and become the right-handed version. And so if we look at like ancient amino acids from Jurassic, they're racemic as well, even though the dinosaurs were building proteins very much like we are with using the left-handed ones. You can actually use amino acid racemization as a geochronometer because it kind of flips on a known time scale. So if you get an ancient organic terrestrial biologic sample and it's like 75% L and 25% D, you can figure out how long it's been going through the racemization process. So we don't know if it was a preference, if there was a preference to produce the left-handed versions on Bennu's parent asteroid, because they probably racemized over time.
All right, and then a few comments. It just says, awesome presentation, fantastic, and congratulations, I would say, to your team for a fantastic mission.
Thank you very much. Yeah, it was definitely a team effort.
And that's it on Zoom.
All right.
Terry, anything on YouTube?
Do we have
we have
online comments?
we have one from YouTube. It just says, fantastic, thank you, really great compliment to the book. So tell us about the book.
Oh, yes. So I published a memoir about a year ago now. The paperback just came out, actually, called The Asteroid Hunter. It's a personal journey of mine. So it starts here at the University of Arizona in 1992 when I was, wandering and trying to figure out what to do with my life. And I got a undergraduate NASA space grant research project, and that set me on my path into planetary science. So I hope you get a chance to pick it up. There's an audiobook version. A good friend of mine and a good friend of David Eicher's here, Sir Brian May, narrates a few of the interlude chapters for me on there. So Brian, the backstory of the asteroid hunter, and I took some liberties here, is that there's two carbon atoms that were formed together in a star, and one of them's in Bennu and one of them's in me, and they're trying to reunite. So that's the underlying theme, and Brian narrates that very short sections. Otherwise, it's a kind of a personal account of the mission from the very beginnings in 2004 to in the paperback, a bonus chapter on some of the sample analysis results as well.
And I do have one other comment on Zoom. I'll just I'll let you know. It's from Dale. It says, you were led to Bennu as a possible candidate for investigation, and it proved to be all that we may have hoped. Congratulations.
Yeah, thanks, Dale.
Thank you so much, Dr. Lauretta. Your presentations are always so wonderful, and we appreciate it every time you come.
My pleasure.
So we hope you're coming back again in the future to talk to us another time.
Yeah, we got some really fun stuff happening in the Arizona Astrobiology Center, so stay tuned.
Wonderful. Thank you so very much. So Terry has a comment.
Yeah, the Arizona Astrobiology Center is just right at Cherry and University. And yeah, right next door. And it's I assume you can go in during normal business hours, right? Yeah.
It's very student focused. The students love astrobiology. Can't get enough of it. They're looking for ways to get involved. It's very heartwarming. And we have astrobiology ambassadors.
Terry, we can't hear on Zoom.
You want to do a. Thank you. Yeah, we have a group called the Astrobiology Ambassadors, and if you have a community event or you want somebody to come and visit your school, we have all kinds of curricula and hands-on activities. We're usually at the Festival of Books, science fairs, SACNAS, all kinds of venues, and the students love to get out in the community. So reach out if you have an event you would like the Astrobiology Ambassadors to show up and get everybody excited about the search for life in the universe.
Wonderful. Thank you so very much for that announcement as well.
Yeah, we had some at the park at last month, the Astronomy Festival. So it was great. Yeah.
Great. Okay. So our usual thing to do at this point would be have Dr. Kokoschka give his monthly planet report. but he's out of the country at the moment. And he wanted me to let you know that he has posted his planet report on our website. And so anytime you want to look it up, just go to the website and you can get the current information there. We also then, I think Doug Smith has a couple of presentations.
You want to keep
Announcements.
YouTube audience on, or do you want to say goodbye to them?
Pardon?
Do you want to keep our YouTube audience on, or do you want to say goodbye to YouTube?
Well, I think we could probably say goodbye to YouTube now and thank people for coming. We really appreciate it when you visit us, and this, of course, this meeting, as our other monthly meetings, are posted. And so we have a whole series of wonderful presentations that are posted that you can listen to. Thank you so much for joining us, and we're here every first Friday